Hi everyone, in this video I'm going to continue with the introduction of systems of linear equations and get a little bit more into the algebra of them. We've talked about linear objects in the context of lines, planes, and hyperplanes. All of those objects are called linear because there's no curvature to them. Equations that describe these objects are shown here. Ax plus by is equal to c is an equation of a line in R2. Ax plus by plus cz is equal to d is an equation of a plane in R3. And the last one there is an equation of a hyperplane in R4. What makes them linear algebraically is that each of the variables is at most being multiplied by a constant. We're not squaring a variable or square rooting it. We're not dividing by a variable. And we're not multiplying two variables together. If we were to do any of those things, like divide by a variable, so say in the first equation if we had a divided by x, or if we had ax squared, or a times the square root of x, or a times x times y, if we were doing any of those things, then what we would be creating is an object with curvature. We'd be creating a nonlinear object. So circles, spheres, cylinders, cones. X squared plus y squared is equal to 4 is a classic nonlinear object that you've seen. It's a circle. The circle has radius 2. The one in the middle, on the bottom there, x plus 5 tan y is equal to 2. I don't know what that looks like, but whatever it is, it's not linear because it's the y variable is being plugged into the tan function. One of the trigonometric functions that's definitely not linear. It's wavy. And the last one there is completely horrifying. It's filled with x's and y's and z's, and look at what's being done to them. So x is being squared, the z is being cubed, and then they're being multiplied together. This is highly nonlinear. What we will do inside this course is we'll examine only linear objects. Objects that look like lines, planes, and hyperplanes, and collections of those objects. We will not examine situations where the variables are being squared or exponentiated. We will not be putting log functions, exponential functions. We're plugging variables into the cosine function. We won't be doing any of that. That's not part of Math 1229. Often when we talk about systems of linear equations, we will use subscripts to indicate which position we're in. So maybe the coefficients or the constants in front of the variables will be indicated like a1, a2, a3, up to an, where n is the number of unknowns, or the number of variables. And then our variables are indicated as x1, x2, x3, all the way up to xn, where we have n unknowns or n variables. Sometimes some of the coefficients can be 0, and they won't appear in the expression. We'd have to infer that. So for some examples are given on the left-hand side, and the last one there on the left, we have 2x2 plus 3x4 is equal to 0. That implies that there is an x1 and there is an x3, and they're not showing up because in front of those variables is a coefficient of 0. So we could rewrite this expression as 0 times x1 plus 2 times x2 plus 0 times x3 plus 3 times x4 is equal to 0. That has to be the way that it truly is in the background. We have to infer that by the absence of components in the expression corresponding to x1 and x3. And then there's some more on the right-hand side that are pretty much the same idea. You can infer the absence, except this last one. This is kind of mean. We won't do that to you. If there's only 3 coefficient, or if there's only 3 components showing, then we would have to give you some hint that there's a 4th one. You can't just throw that in there. There's lots of vocabulary in this part of the course, very new vocabulary for you. One thing is if we took a bunch of those equations, those linear equations, and we made a stack of them and made sure that in that stack all the equations have the same number of dimensions, or the same number of variables, that stack would be called a system of linear equations, which we will abbreviate with SLE. A system of linear equations will consist of some number of equations, which we'll call M, so how high is the stack, and a number of variables in each equation, which we'll call N. So do we have an X and a Y and a Z, so that would be 3. N is equal to 3. Or do we have maybe 5 dimensions, 5 variables, so in that case N would be 5. It's a matter of special caution to not mix up the number of equations with the number of variables. we can have, let's say, 10 equations and only 5 variables. When we talk about a solution to a system of equations, what we're really talking about is a set of numbers which we could put into vector form, which is ordered, where each number corresponds to the value of the variable. But if we plug all such numbers into all such equations, we'll have left-hand side equaling right-hand side. So it's like a key that unlocks all the doors at the same time, where each equation is a door. The term standard form is what we've already been doing for lines and planes that we've called standard form. For a linear object to be in standard form, we have to have ax plus by plus cz is equal to d. We have to have something that looks like that, where the components are written in order. So x comes before y, or x1 comes before x2, and the constants are on the right-hand side of the equal sign. If any part of that's missing, if any part of that's wrong, then our expression is not in standard form, and it's going to be very important in the new material that everything that can be put into standard form is put in standard form before we do anything else. The term consistent means that the system of linear equations actually has at least one answer. There's at least one key that opens all the doors at the same time. There's at least one x, y, and z coordinate, or a set of values that we can plug in to make left-hand side equal right-hand side. And it's the same set for all of the equations inside the system. That's important. And there could be more than one. There could be 2 keys that open all the doors. We'll talk about that. The word inconsistent means that there's no key that unlocks the door. There's no x, y, and z value that we can simultaneously plug into all of the equations inside the system that will make left-hand side equal right-hand side. I'm going to go through a set of examples, and it might be a little bit confusing because I'm not actually going to solve them properly. I'm just going to say some things about them. The first expression here, x plus y plus z is equal to 4, x minus y is equal to -1. This is linear because all that's being done to the variables, the x, the y, and the z, is they're being multiplied by constants. So in the first equation, they're all being multiplied by 1. In the second equation, the x is being multiplied by 1, the y is being multiplied by -1, and the z is being multiplied by 0. So they're all linear. They're all in standard form. We can say that it's 2 equations with 3 variables. So this is a 2 by 3 system of linear equations. So again, linear, standard form. It has everything where it's supposed to be. The x's and y's are in order. The constant is all by itself on the right-hand side. And it turns out that it's consistent because we can find at least one solution. And here is one such solution. That x equals 1, y equals 2, and z equals 1 makes left-hand side equal right-hand side. We can check that. Let's look at equation 2. X minus y is equal to -1. So let's plug in 1 for x, 2 for y. 1 minus 2 is -1. We get -1 on the left equals -1 on the right. So equation 2 works. That is a key that opens that door. Let's look at equation 1. Does that key also open that door? So 1 plus 2 plus 1 equals 4. Is that true? Yes. So that key also opened the first door. Since that key opened both doors, it is a solution to the system of linear equations. Since the system of linear equations has at least one solution, we call it consistent. Doesn't mean that there's not other keys though. There might be another solution that will work. And there is. Here's another one. 6x plus 2y is equal to 4. 3x plus y is equal to 0. So this is saying that if I buy 6 apples and 2 bananas, it'll cost me $4. And if I buy 3 apples and 1 banana, it'll cost me $0. Something's fishy about this. But let's look at this, all the different pieces, all the different vocabulary, all the different terminology. We have 2 equations with 2 unknowns, so this is a 2 by 2 system of linear equations. They are linear, which I should have said first, because look, nothing's being done to the x squared, or nothing's being done to the x, nothing's being done to the y, except they're being multiplied by a constant. They're not being squared or square rooted or anything weird. So linear, standard form. Is it consistent? No. There is no solution to this. Look at equation 2 again. It's essentially half of equation 1. So the first equation is saying how much would my bill be if I purchased 6 apples and 2 bananas? My bill's gonna be $4. If I cut my order in half, if I buy half as much stuff, it really should be $2. It should be 3x plus y is equal to 2, but it's not saying that. It's saying it's equal to 0. So something's defective with this system of linear equations. It's inconsistent is the terminology that we will use. There's no solution. How about this one? I don't even know why I'm pausing because no one can answer, but it's not linear. Look at the 3 to the power of x. We have a variable that's not being multiplied by a constant. It's being exponentiated. And we have, look at the next one in the second equation, cos of y. That's not linear. We're plugging the variable y into a function, into a function that's going to do something horrible to it, something very nonlinear to it. So this system, this is a system. It's 2 equations with 3 variables, so it's a 2x3 system of equations, but it's not a system of linear equations. And good luck solving it. If you want the solution or solutions to this system of linear equations, that's a whole other ballgame. That's like, you don't want to go there right now, and maybe not ever. Here's another one. What do you think? X plus 2z is equal to y over 2. Y is equal to 2z. It's a system. How many unknowns? How many variables? Well, okay, first it's a system of 2 equations. How many variables? We have an x and a y and a z. So it's a 2x3 system. Is it linear? You might be staring at that y over 2 and thinking, no, because you said it has to be multiplied. And that's not multiplied, that's divided. But what is division if not multiplication by the reciprocal? What did I just say? What I said in English is this. I can rewrite this expression as x plus 2z is equal to 1/2 times y. That's completely equivalent, and now I've converted it into multiplication. That means that this is linear. We're not doing anything non-linear to the variables. We're just, in that last thing, we're multiplying y by 1/2 and just writing it as a division. But it's the same as multiplication. Okay, so it's a 2x3 system of linear equations, but it's not in standard form. We don't have the x plus the y part plus the z part equals a constant. It's all mixed in, it's all jumbled together. We can fix it. I'll show you how to fix it. It's x minus 1/2 y plus 2z equals 0. There's no constant piece. And then the second equation is 0 times x plus 1 times y minus 2z is equal to 0. And we can prove there's a solution. For example, x is 0, y is 0, and z is 0. That key opens both doors. Replace the x, the y, and the z in equation 1 with 0, and then do the same thing in equation 2. Replace all the variables with 0. You'll have left-hand side equals right-hand side. So it's consistent because we found at least one answer, and actually there's more answers. There's an infinite number of answers for this one. And I'll show you how to do that. I'll show you how do you know there's an infinite number? You found one by like just staring at it, and how did you do that? Well, I'll show you how to do that without magic, like to do it in a reliable way, in a systematic way. Okay, so let's look at this one more closely. The x plus 2z is equal to y over 2, and the y is equal to 2z. We're going to put this into standard form, which I already did, so I'll just copy that. X plus, x minus 1/2 y plus 2z is equal to 0. And then the second one was, I won't write the 0 times x, I'll just leave a blank there. You're allowed to do that, still standard form, but I'm going to write it in a stack so that the y part for one is underneath the y part for the other one. And the same for the z part. This is a nice visual cue to keep track of the fact that my second equation has a 0 times x in it. It'll just remind me of that fact. Okay, so that's part A. Part B. Show that any vector of the form -3, 6, 3 is a solution. It shouldn't say of the form, but what it means is that you can multiply. Oh, I won't get into that. It's jumping too far ahead. I'll just show this as a solution. Keep things simple. So I'm going to replace x with -3. I'm going to replace y with 6. I'm going to replace z with 3 inside both equations. So inside the first equation, we have -3 minus 1/2 times 6 plus 2 times 3 equals 0. Is it true? So let's simplify. We got -3 minus 3 plus 6 equals 0. We have 0 is equal to 0. True. So far, so good. Let's look at the second equation now. So we have 0 times -3 plus -6, sorry. Y is 6, so 6 minus 2 times 3 is equal to 0. Is it true? 6 minus 6 is equal to 0. It is in fact true that 0 is equal to 0. So that key unlocked both doors. It's a solution. Thus, -3, 6, 3 is a solution. Part C is the interesting one. Part C is saying there's actually an infinite number of solutions given by -t, 2t, t for any value of t that you want. This is like, here's all the different keys that will open the door. You can't use any key in the world. There's an infinite number of them, but they are all related to each other in this particular way. How do we prove it? Well, I'm going to substitute in exactly what it says. In equation 1, we're replacing the x with a -t, and then the y with a 2t, and the z with a t. And then we'll check, we'll simplify. We have a -t, and another -t, and a plus 2t is equal to 0. And this says that 0 is equal to 0, which is true. And now we'll do it for the second equation. I'm going to replace y with 2t, and then minus 2 times z, so minus 2 times t is equal to 0. And that's telling me right away that 0 is equal to 0 is true as well. Thus, -t, 2t, t is a solution for any t. And actually, part B is a particular value of t. That's what happens if t equals 3. I'll say notice, just so it's a little bit clearer. Notice this is just part C with a particular value of t. Okay. We'll talk about families of solutions in the next video.